Okay. No, let's use red. Hello. Welcome back to this part two of neural networks and clustering. My name is Chieh. I'm from Northeastern University. And the last time we talked about this concept of autoencoders. And I think this is where we left off, right? Well, autoencoders essentially is a way of encoding the data. And once you encode the data into a low dimensional space, something like this, we can then do clustering such as kmeans on top of it. And that's is basically the simplest way to do clustering and neural networks. However, this is not that interesting. I mean, the idea is pretty obvious. I mean, this is so simple. We run autoencoder, get f of x, and then run kmeans. Like, that's it. Like, what's so special about doing this? Well, actually nothing. There's nothing special. But today, I'm actually going to go over k-means. Everybody should. I'm going to assume you've seen k-means before, but because I like to tell you things you already know, so we're going to go over it anyways. And because I'm the master of obvious, and this actually, there's a reason why I'm going over k-means again. Because it's going to lead into the first paper that I'm going to talk about. So, what is k-means? Well, k-means is a way of clustering data. Right? You have two sets of data together, and you wanna cluster the similar ones into the same cluster. So let's say we have some kind of data X matrix, and each sample is just a single row. And we want to transform this X into some kind of Y. And the Y is going to be, so this is going to be 0, 1 if it's the first cluster, and this one will be 1, 0. So 1, 0 will be the first cluster, 0, 1 will be the second cluster. And we want to find the Y such that the cluster designation exists for every single data set. That's what we want to find. And we don't know the centers, but let's assume in each cluster there's a center, which I'm going to call C1, and then I'm going to call C2. And given that I have two clusters, it's just C1 and C2, right? And I'm going to stack them together and call this stacked version C. Next, what I want to do is I want to multiply Y and C together. So remember Y is right here, which is just the cluster designation, which of course we don't know. And then there's the C, which is the centers, which we also don't know. But let's assume for now that we know them. And if we know them, which implies that when we multiply them together, we'll get another matrix. And this matrix here, like, there's going to be n of them because they're n samples. Essentially, this tells you x1, this is the center for x1, center for x2, center for x3. So this matrix here tells you the center of every single sample that you have. And so this C hat, right? I'm going to call the multiplication of this C hat. So C hat is the cluster center for each data. And the dimension is going to be n by d, where d is the dimension of the data, n is the number of samples. So in k-means, what we want to do is we want to find the centers, right? We want to find the centers so that the distance between each data is minimized. Again, I'm going to say this again. We want to find the centers that minimizes this expression here. Which, what this expression means is we have each center, we want each x subtract to its corresponding center to be minimized. And that's what we're doing in k-means. And the way we solve k-means, which, again, I'm going to assume you guys know, is essentially we pick some random center and then we pick the x's that's closest to the center, and that will tell us the y matrix. Once we know the y, right? So we know all the x's for this one, and we know all the x's for this one. Then we just average the x's to get the new center. So we get a center from that. And using the center, new center, we go back and find all the closest x's again. And we essentially go back and forth, and that will solve this problem here. We pretend we know this, we get the best ones, then we calculate the center again, and it goes back and forth. Right? And that's k-means. What I want you to know from k-means is this formula here. The procedure, I think most of you have seen and heard of the procedure, but the part I really want you guys to see is this formulation. Because this leads into our next idea. In 2013, Song et al., in his paper called Autoencoder-Based Data Clustering, which is the first paper I'm going to talk about, essentially combined these two ideas, right? He combined the idea of autoencoder with k-means. And you might be wondering, isn't that what we just did that? We did autoencoder and then we did k-means. No, not exactly. We did them separately. What he did, what Song did, is that he combined them into one single formula. So right now there are two separate formulas. Song et al., right here, essentially combined them into one formula. Like, why be different if you solve them separately versus solving them simultaneously? And this is because when you do dimensionality reduction, which is what autoencoder does, it's not trying to give you a new dimension, it gives you a lower dimension, but the lower dimension doesn't care about whether it's good for clustering or not. It only cares whether it's a low dimension representation. So a perfect example, I think, looks something like this. If you have like one cluster that looks like this, another cluster looks like this. Now, if you do some kind of dimensionality reduction, it's going to put everything here, right? If you put everything right here in the center, you can no longer, you can tell them apart because you just essentially merge them in one. So just because you put something in the low dimension, it doesn't mean it's low for clustering. Yeah, this right here will project down, so everything will end up right here. So therefore, if you solve them simultaneously, it's going to try to do dimensionality reduction. Make sure that the dimension you find, the lower dimension, takes clustering into account. That's why it's more it will give you a better result. Now with autoencoders, right, we're just matching the input and output, like input and output, and we wanted to use the bottleneck part right here. I'm called f of xi, and now we use this part with the k-means, and the new equation looks something like this. We want to find the centers and the weights, such that here's the autoencoder, and over here is the centers. Remember, here used to be x, right? Instead of x, that's minimizing with the centers, we are using this function that's minimizing with the centers. And by doing this, right, all we have to do, we're still solving it similar to k-means. We essentially first find some random c, and then we can use stochastic gradient descent and solve the rest of the problem. And of course, we go back and forth, and that will solve this type of problem. I think there are more details to it, but the key is essentially to understand what they're trying to do, which is to combine the autoencoder, and then as well as the idea of k-means. And this variable here, lambda, you might be wondering, is a weighing constant. And what a weighing constant does is, if you make this value very large, it means this is more important. And when you do optimization, it's going to take this part more into account. Or if you make this very small, so small that it's 0, for example, you're only doing the autoencoder. So this is kind of like a design choice, which one you want to make more important. Okay. Now, like I said, you use the same steps as kmeans to solve this. Take some center and then do some stochastic gradient descent, and you can now solve this. So the idea is pretty simple. Just autoencoder with kmeans. And I think that's enough for today. I think with the next video, I'll go over the 2014 paper with Chieh and Itao. I think it was published in Triple AI, and it's called Learning Deep Representation for Graph. So, okay, well, thank you very much. Talk to you later.